Okay, so the first three did not record like I wanted them to, so we're just going to start at 4. Most of us should have this anyway, or the first 3 we should have. So number 4 actually would have been very similar to number 3, where instead of a parabola, you were given the cosine curve, and then that curve was only defined from a negative pi over 2 to a positive pi over 2. And then we know the cosine crosses the y-axis at 1. And then the negative pi over 2 and pi over 2 are zeros for that graph. And what we're doing, instead of a rectangle inscribed inside of a parabola, it's now inscribed inside of this cosine curve. And what we're trying to do is create the biggest rectangle possible and see if we can use up as much space enclosed between the parabola and the x-axis as we could. What we're again looking for, we're trying to, in terms of the base of the largest rectangle possible. So what we always want to identify is what are we trying to do? And in this case, we're trying to maximize the area of a rectangle. So since we want to maximize the area of a rectangle, that's how we get this started, with the idea that the area of a rectangle is our base times our height. We then want these to be the same variable. So just like number 3 above, wherever I put that green line, whatever that x value is, my base would have to be twice that x value. And then the length of this green height here would have to be whatever the y coordinate was at this particular point. So the y coordinate is your height. So our height is the y coordinate, but we don't want to introduce a different variable than the x that we had for the base. So instead of y, we just take what y was equivalent to with respect to x. And in this case, it was a cosine of x. So that's our height. That then allows us to say that the area is our base times our height, and our base is now defined as 2x, and our height is now defined as cosine of x. That's then what we want to take the derivative of. This is a product, so understand that. It's the 2x times a cosine of x. So when we go to take our derivative, we do the derivative of the first and leave the second. Initially, we're going to say plus, because that's what we do with the product rule. You leave the 2x alone, and then the derivative of cosine is a negative sine of x. As we set that equal to 0, we'll simplify it a little bit. This really just becomes minus 2x sine of x. We then think, is there anything that makes that derivative undefined? There isn't. We then understand, similar to one that we had done earlier in the notes, if I try to solve this by hand, that's going to keep you busy for a very long time. So what we're doing is we're graphing this into our calculator, and we're calculating the 0 on the calculator. If you wanted to try it, feel free. If not, understand when I graph this, we also have an interval. We're only concerned about this interval up here, the negative pi over 2 to the positive pi over 2. So when I show you what this looks like on the calculator, if you look at my window, I went ahead and made my x minimum a negative pi over 2 and my x max a positive pi over 2. When we then graph that equation, here's what it looks like. Understand this is our derivative graph. Because it's our derivative graph, we're looking to see where did the derivative change from positive to negative in order to get a minimum or a maximum. So this point here is a min, because that's us having a derivative go from negative values below to the positive values above, and then our derivative is positive, 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 positive until we hit here. That's where our derivative is 0 again, and we change from positive values to negative values. So this 0 is the x value that would maximize that rectangle. So I'm going to do second calc 0, the left bound, so we're to the left, set your right bound to the right, guess, and we should get 0.86. So when we go back, where is it? No, this one. Our x value should be 0.860. If that's our answer, great. In this case, we need a little bit more work though. The question is asking you to find the base. Our base is twice the x value. So our answer is really 2 times that 0.860. All right, that would be our answer, whatever that is. All right. All right, next problem. We're going to skip 5 altogether, so don't worry about that one at all. 6 and 7, though, definitely will help you with the assignment. All right, so number 6, it says the U.S. Postal Service will accept a box for domestic shipment only if the sum of the length and its girth, which is the distance around, does not exceed 108 inches. The question is then asking what dimensions will allow a box, so once again a box, with a square end to hold the largest amount of material as possible. So we are again trying to maximize the volume of a box. So for sure, we're going to be doing our length times width times height again. Let's go ahead and try and draw this box. Now this is an actual box, a completed box. It's not a flat surface that we're turning into an open top box. So we're going to draw in a box and we want it to have a square end. So I'm going to try to draw my square. That's a bad square. Let's try that one more time. It's a little better. And then let's draw in a box with a square end. Don't judge. Not an artist. This here. There. No, that's just bad. Let me pause this a minute. I'm gonna practice this a second. All right, so now I just practice this, so hopefully this will be a little better. So I'm gonna draw it like this. It looks like a rectangle. Like that. And then our ends are squares. There, it's a little better. I'm a little more proud of that one. So similar now, we want these to be the same variable, length, width, and height to all be the same variable. What we were told is that this is going to be a square end. So what that allows us to do, when we go to label these first, actually, let's call this our length, that's our height, and then this here would have to be our width. The fact that we're going to have a square end means that, let me try as best I can, the length around this here, that's our square end. And if it's a square, then our height and our width have to be the same. So the H and the W have to be the same. So what I'm going to do is I'm going to go ahead and let my height be W. So I'm going to get rid of this here. Instead of a height, the width and the height have to be the same. So I'm going to call that a W. And if I let my height be defined as W, then I can let my width just be itself. The W can be the W normally. So what that has now done, the height, this W is here, and then the width we've accounted for here. We still need to somehow get our length with respect to a W. The way we're going to do that, it says the sum, one of our restrictions is the sum of the length and the girth cannot exceed 108 inches. So what that does is actually sets up a different little equation. So the sum means we're going to add the length plus the distance around our box. So look at my orange dotted line that I have here. The distance around our box would be this W, this W, this W, and then this little W there, all added up together, so that when we do the length plus the 4W, it cannot exceed 108 inches. So even though this sets up as kind of an inequality, cannot exceed 108, since we're going to maximize this, we would want to use up as much of that as possible, which would be the full 108 inches. So the distance around the box is the 4W. We're going to add that to the length, and we're setting that equal to the 408. What that then allows us to do is solve the length for L, so solve that equation for L. And then you see the length is now defined as 108 minus 4W, so that we can then come up here and define the L with respect to the variable W as well. That then allows us to now write our volume equation as 108 minus 4W multiplied by W multiplied by W. So it's just our length times our width times our height. Clean that up. So that thing, when we completely simplify this, would be 108 W squared minus a 4W cubed. That's our equation to take the derivative of and find our max. So we do that. So 216W minus 12W squared, set that equal to 0. We can pull out a 12W from each. That leaves us with 18 minus W. So 0 is a test point. However, we can't have negative links, so there's really no need to go to the left of 0. And then 18 is our other test point. If we now test these values in our derivative, if I plug in, let's say, a 10, 18 minus 10 is positive. A 10 here is going to be positive. If I come over here and plug in a 20, 12 times 20 is positive, but 18 minus 20 would be negative. So that 18 for our width would be what we would want in order to maximize the volume of our box. So we would want our width to be 18 inches. The question is asking what dimensions, so we want all three of them. Well, our width and our height had to be the same, so that's got to be 18 inches. And then our length, all we need to do is now, here's our length over here. Let your W be 18, so 4 times 18 is what, 72? And then 108 minus 72 should give us 36 inches. Those are the dimensions we would want to use to make that box as big as possible. All right, the last one. Another classic problem here where you have a rectangular field is going to be bounded on one side by a building. So if I write the word building, so here's my building. And then we have this fence that's going to be bounding this field, but we only need the fencing on 3 sides because the building is bounding it on the 4th side. You have 3,000 feet of fence to get to use. And using those 3,000 feet, we would obviously want to create the biggest field as possible. So the question then is, how could I maximize the use of the 3,000 feet of fence to create the biggest field as we could? So when this says the largest field that can be produced, what we want to do is maximize. Think about this as a flat surface now. This is not a box like we've been dealing with. It's a flat surface. So we're just maximizing the area of a rectangle. Largest field, the field would have an area, not a volume. The area of a rectangle. Before we use base times height, I think when we're talking about the ground as a flat surface, length and width would work better. Not that you can't use base times height, but we're going to use length and width. We want to get these defined using the same exact variable. So the way we're going to go about that, let's come over here. Here's our length, here's our width. So label that. And then the way we're going to be able to do this, if we go up to this part here, we have 3,000 feet of fence to be used. Think about where we're going to allocate those 3,000 feet. This is fencing, this is fencing, and this is fencing. So we have those 3 lengths all added up have to equal 3,000. So that's where we get our equation from. This is a W, here's a W, and then we also have the length. So the length plus the 2 widths better equal the total amount of fence that we have to use, which is 3,000 feet. You could solve for either one of these, the L or the W. We haven't defined any of them up here yet, but I would think it would make the most sense. The easiest is just solve for L. So L would be 3,000 minus the 2 widths. So that's what we define this as. So if you now notice, the length is defined using the variable W. So there's no reason for us to change the variable down here. The W can be itself and just be a W. We can now take this equation. The area is our length times our width. Our length was the 3,000 minus 2W. Our width, we said, was just a W. As I've said, we want to simplify this before taking your derivative, just because it makes our work a little bit easier. So we distribute that W. And then now we find our critical points with the derivative. So the derivative is 3,000 minus 4W. That's not going to be undefined anywhere. So we set it equal to 0. We can pull out a 4 from each of those. and you're left with 750 minus W. We'd probably want to confirm that that's our max. So 0, we can't have a negative length, and then 750 is our test point. We'll make it obvious, we'll pick a 1. 750 minus a 1, definitely positive. If we pick 1,000, 750 minus 1,000 is going to be negative. That 750 is in fact our max. The question is, find the dimensions again. So what we just found, 750 is our W. So we would want our width to be 750, so 750 feet. Our length we can find right here. So just let your W be 750. So 2 times 750 is 1,500. 3,000 minus 1,500 is 1,500. So that would have to be our length. Look those over. There's going to be 2 or 3 problems on that assignment that are pretty nice, and there certainly is going to be a couple that you would probably have some questions on. So try to get the nice ones done, and then on Monday we can discuss any questions that you have on the ones that you find to be a little bit more difficult. All right, with that, that's it. Have a good weekend, and we will see you guys all on Monday.